I'd like to introduce the speaker for this session, Professor Vikram Dayal. Sir is a professor at the Institute of Economic Growth and works in the Indian Economics Training section of the Institute and teaches public economics. After completing his master's in economics from the University of Colorado, he received his doctoral degree from the Delhi School of Economics. Sir has been using the R software in teaching quantitative economics to diverse audiences and is the author of the Springer Brief titled An Introduction to R for Quantitative Economics, Graphing, Simulating, and Computing. He has published research on a range of environmental and developmental issues using graphing and computing techniques. Today, Sir is here with us to give us an insight into the role of data sciences in academic research and conduct an informative session on the use of our software. Over to you, sir.
Thank you for inviting me. The Economic Society is very impressive and things have changed a lot, very dynamic, and really makes me feel old. You all got so much energy. So I hope I've got something useful to say and pitched it at the right, at the audience in the right way. So I'll share my screen now. So can you see my screen?
Yes, sir.
And can you hear me?
Yes, sir.
Right. Right. So I'm going to talk to you about what you can do with R. So what can you do with R? The short answer is a lot. And this map, for instance, was made with R. So in the first section, it's going to be a little dreary. I'll just speak a bit about data science and code and the workflow in R. So this would be somewhat helpful for those who are new to R or who don't know R at all. But it may be very familiar and a repetition for those who already know R. Now, in a piece in 2009, Hal Varian, who was then the Google chief economist, wrote that the ability to take data, to be able to understand it, to process it, to extract value from it, to visualize it, to communicate it, that's going to be a hugely important skill. So he said that you have a lot of data, so the scarce complementary factor was the analysts, the economists. So this is what Varian was saying. What's notable is that this, I think, given that in economics, we don't often talk about visualization or communication. Coming from Varian, who I guess most of you have read his textbooks, is a major statement about the importance of data and data science. Just one sec, please. Hello. Sorry, there was a bit of a disturbance. So the first point is that R is very good for the data analysis workflow. And we got this from this schematic of the data analysis workflow. We have this due to Hadley Wickham. So we have the import of data that is then tidied. Then we transform and visualize the data. And this transforming and visualizing is interacting with modeling. And this blue circle is called exploration. And then we communicate the data. So R is very good for this entire data analysis workflow. And as you know, these days you have firstly a lot of data and also a lot of variety of data. And this part is often very tedious and painstaking. And we call this data wrangling in data science. The other thing is note the emphasis on visualizing the data and also on communicating the data. So this is, again, in data science, it's not like it's a well-defined thing. Perhaps just as, in a sense, econometrics is not well-defined always. So Peter Kennedy said that econometrics could be defined as what econometricians do. So data science, this is one perspective from Hadley Wickham. And he's the author of this tidyverse package, which is currently very popular in R. Now, I would encourage people to use the R Studio. Currently, it is the way it is very popular, and it is a state-of-the-art environment. It makes working in R much easier. So when you open R Studio, you have these 4 panes. In one, you have the plots that appear. The R script is where you can save your commands as a single text file. Then the output of the commands you run appears here. And you can import the data from this tab, and the history tab shows the previous commands. Now, code records every step of your work. Why code? That's an important thing. So you could run something in Stata without writing code, but even in Stata, if you're going to do a lot of data analysis, it's very helpful to write code, because you keep a record and your work is reproducible. This blog entry in 2013 spoke about the Reinhardt-Rogoff error, both very prominent economists. And it's titled The Reinhardt-Rogoff Error, or How Not to Excel, and deliberately the play is on Excel at economics. So in data science, there's some amount of disdain for Excel and the lack of reproducibility of Excel. So further, this blog says that in this famous 2010 academic paper, which was very influential in policy circles, this paper contained significant errors. And according to the writer of this blog, this is due to the pervasive failure of scientific and other researchers to make all data and computer code publicly available. So that's the reason for coding. Also, in the private sector or in the data analytics world, I believe, I haven't experienced it myself, but I can see that if you are in an organization and you're working in a team, then coding obviously helps you work together and keeps a record. Also, let's say you're doing a certain analysis on a regular basis, the data is continuously coming in. So as the data comes in, you keep producing updated outputs. So then code is very helpful in that sense. Now, typical R code works like this. You create a new object. You use a function which acts on an object. There's certain information which is passed to this function related to the object, and you have certain options. An example of this is where we create a vector price, and price, we can assign these values 21, 31, and 34 to this vector price in this manner. And this is C, this is the concatenate function. So this is how typical R code works. And R is called an object-oriented language because as you go along, everything becomes an object. Data set is called a data frame, so that's an object. A regression model is an object. A plot can be an object, and you're constantly using functions. So it's called a functional programming language. I don't know the deeper implications of this like a programmer would, but it's worth pointing that out. Now, the great strength of R is the collection of packages. So R is the outcome of this global movement, open source movement. Although it began with two statisticians in the University of Auckland, uh, Robert Gentleman and Ross Ihaka. So Ross Ihaka retired as an associate professor, it seems, even though he designed this language. So they adapted the earlier S plus for their students. But then someone along the way convinced them to make it open access. And then that led to this huge success of R. And there's a whole ecosystem or collection of packages which you can access. So it's like a global public good. And you have people all over the world who contribute these packages. And now there are thousands of R packages. And so that's really the strength of R. Note that this is, since we are economics students, the model is quite different from something like Stata, which is a corporation and you have paid employees. So here, I suppose many of them would be statisticians or whatever, perhaps many in the academic world. So, but they don't get their funding through their contributions in R. One of the most popular packages, and this is called the tidyverse, which is actually a collection of packages, so like a meta package is the tidyverse. And currently it's one of the most popular ways of using R. And it has led to some extent to a revival of R. So for data science, many people say with the tidyverse, R has a real edge. But in any case, I think beyond the point, it's not very productive to compare packages. If you're a full-time data scientist, you probably know more than one software. And younger people these days, in any case, should learn several software. But it's good to have a strength in one of them. Now, the tidyverse package is popular. You need to install the package once with this command, install.packages. Once it is installed in R, we can load it with the library command, library tidyverse. Okay, I just want to check at this point whether you can hear me. Am I audible? Because that's the problem with online.
Yes, sir, you're perfectly audible. We can hear you.
Okay, thank you. Apart from the fact that since I'm at home, there are people walking in and I have to shoo them away. You can do a lot with the tidyverse. So, for example, you load it and then you can get your data into R. Now, there are various ways of working with R, but you can also use the tidyverse command read_CSV. This is the name of the file, and then it gets converted into an object with which you can work in R. You can plot the data with this ggplot package. This is currently the most popular package in R and perhaps one of the most popular packages ever. Millions of people download it. And this is also almost like one of the major reasons some people use R. So some people use R just for plotting, and then they often use ggplot. And there are lots of packages now which build on ggplot to do further visualizations. So this is how the typical ggplot command works. This is the data. Then you say within this data set, which variable you want to plot and what kind of thing. So if you want a histogram. This is not related to the tidyverse. This is the basic R syntax for regression. So this is the most basic regression, like you have reg in Stata. You create an object reg.mod, you regress y on x and z, LM is for linear model. Now, R has very good regression facilities. So in certain domains, Now, for a while, for example, in econometrics, R had a fantastic, it was a, the time when structural breaks were, the vogue. Every now and then there is some new technique and it's newish, and then people start using it because you can get your papers published. So at one time, there was a structural break buzz, and people were using the struct change package in R, which was even more advanced than what you had in other packages like Stata and eViews. Because R is an ecosystem of packages and people all over the world can contribute, they're not shackled by, in a sense, the structure, say, of a corporation. So, if I'm a structural break expert and I know coding, I can contribute this package to R. R is also very good, for example, for Bayesian econometrics and so on. And one of the things I found is that a lot of PhD students get into R because they discover that there's some estimator they want to use, which happens to be in R. So I've had 2 or 3 friends who had PhD students, and then they discovered that R had something like that. Okay, with that kind of preliminary background, I'll just give you some assorted examples of what you can do with R. So these are somewhat visual, and this is one of the most remarkable things about R, I feel, is you can even do maps with R. What is even more remarkable is that I was able to produce this map using just that ggplot, the same ggplot that you will use for plotting histograms, for plotting scatter plots, can be used to make maps with R. With very little overhead. I don't really know any spatial econometrics, spatial statistics, or anything like that. I've never really worked. I've never worked with shapefiles, but I incorporated this world development indicators data. So this is for countries all over the world, the GDP per capita with in logs, base 10. So the redder thing is the poorer countries, and the greener, the wealthier countries, all well known. Now, by itself, this is not the only package which can make maps. There are lots of mapping softwares, but with R, there's a versatility. The thing is, you're not restricted to modeling just the raw data. You could do some analysis in which, let's say, you're doing some calculations for different countries, and then you can use this to communicate your findings to the final client. So that's the advantage of R, the entire data analysis workflow. So that's the thing. You could do some Bayesian econometrics, do some Bayesian BAR, do some projections of next year's expected growth in GDP per capita, and then plot it on the map. You can get the world development indicators data quickly with R. So this is just an example. You can also do that with the Penn World Table. So if you work in empirical growth, at least at one time, or maybe even now, a lot of the empirical work in growth economics uses cross-country data. So you can get the world development. I'm not saying that's a perfect source of data. No source of data is perfect. But as you would know, there are lots of indicators in the world development indicator. So within a matter of minutes, you can get it all loaded into. So you load this package, you install it, you can search for this, and then subsequently you can get all the data. And this was then mapped in R like that. Then another remarkable thing is this whole thing of networks. So you can work with networks in R. And networks are everywhere. I would encourage you to see this video by a person called Barabasi, who's a full-time network academic, professor in networks, about networks are everywhere. Now, this shows, this is the thing. It's a very specific part of the global value added chain in automobiles. This is just for the electrical components, okay? Just for electrical components, not the final thing. It's the components, that to electrical components and the 2016 network. Now, I'm not sure how you interpret this, but basically these are all the flows. So imports and exports which are happening. So there's assembly, then further export, then reassembly or whatever. So people who know trade and industry well would be able to interpret it better. It's by some work by Ameghini and Gorgoni. But one thing that comes out is that you have this was the traditional, so the, the lines are denser here. So this is Europe. So in the 80s and all, Europe dominated this automotive components goods network. But then over time, these have emerged as so you can, there are measures of network, so network importance. So one simple way of thinking of it is number of lines you're connected, which come out or go into these nodes. And this is China, Korea, and Japan. So these have really moved over time, so the trade network will evolve. So there are many things. I mean, there's something in it for the trade theorists, there's something in it for the empirical economists. There's also something in it for, say, policy makers, because this is a wonderful communication device, because we got the network and then we're superimposing it on the global map. And this is just from an ITNR package, 2 lines of code. Of course, the data is all loaded in. Like I said, if you're doing it from scratch, it's going to take time. And probably the data will require a lot of processing, because you've got all these dyadic relationships which you've got to translate into data analysis. This is somewhat easier, and this, of course, you could perhaps do better in one of those things like Mathematica, but you can plot mathematical functions with R. You can also simulate differential equations, etc. Okay, so those are some assorted examples. Now I'll go to some data science proper, and I'll talk about R and causal inference, description, and prediction. So first, causal inference. So in this year's background to the Nobel Prize, it says most applied science is concerned with uncovering causal relationships. The systematic use of RCTs to study causal relationships has resulted in tremendous welfare gains to society. For many important questions, researchers must rely on observational data. So this is, it's not like we weren't doing causal inference, and some argue it's always there in econometrics, but over time it kind of got blurred. So if you open something like Gujarati, for instance, it's not very explicit about causal inference. So 2 frameworks have made causal inference very explicit mathematically. One is the Rubin causal model, and the other is the graphical causal model of Pearl and other scholars. The first, the potential outcomes, the Rubin causal model is now very influential in economics. And Imbens, of course, has worked with Rubin. And Imbens was one of the Nobel Prize winners this year. So R has good packages for doing causal inference, because R is the lingua franca of statistics. So a lot of the core statisticians, or even people, some of the contributions, interestingly, also might come from political science or sociology. So you do have the counterparts of econometricians. So in political science, they're called methodologists, who contribute packages. Now you can do, for example, randomization inference with R. And this is a trend in statistics that we see. It's an old idea dating back to Fisher himself, the person who first thought of actually using randomized experiments. So you rely on randomization into inference. You build on the null hypothesis that there is no difference in the average outcome between the treatment and the control group. So that's your null hypothesis, and you shuffle the data essentially, and you keep re-estimating and you get the randomization distribution. Now this, interestingly, is from the paper by Duflo and Chattopadhyay. They didn't do randomization inference. I've just taken their data and done this just to show that, you know, this is something that you can do with R. The thing is that you tend to make fewer assumptions in randomization inference. But essentially what they found, Duflo and Chattopadhyay, in West Bengal, at the Gram Panchayat level, when certain villages were reserved for female pradhans, those villages had more new or repaired drinking water facilities compared to the control group. So whether the woman who's heading the panchayat is a man or a woman makes a difference to the kinds of investments which are, or projects that the Gram Panchayat undertakes. One of the examples of quasi experimental work is regression discontinuity, and the number of packages in R with which you can do, and some of the things you can do with these packages, I mean, just very interesting. So this is related to the question, did the minimum legal drinking age affect the death rate in the US? So 21. So the idea is that before you're 21, you can't drink. Once you're 21, you can drink. And when you get drunk, when you drink, you get drunk. When you're drunk, you drive carelessly, and you're more likely to have an unfortunate accident. So, but otherwise, so people who are, say, just below 21 and just above 21 are a lot like each other. So people just below 21 might be very different from cautious 50-year-olds or 60-year-olds. So, but here it's, so in that sense, you may have a more, you got a comparison which has got some integrity in terms of causal inference. So this is presented in the book by Angrist and Pischke, 2015. And as you know, Angrist, of course, won the Nobel Prize this year. And this particular estimate is coming from using, in this package, there's a facility. So you can do a non-parametric regression, which, and I find this quite something. You use a non-parametric regression, which incorporates an optimal bandwidth calculation. And that's what imbens. So imbens is this perhaps very less known econometrician, but as you can see, he's been doing lots of this kind of work, and he's also a co-author of Rubin. Now you can do Monte Carlo simulations with R. So Peter Kennedy, who used to advocate, he's the author of econometrics textbook, that if you really want to understand what's going on in R, you should do, or you should think about how you would use a Monte Carlo simulation to address a question. So in this Monte Carlo simulation, we have a variable which is potentially omitted. Now, if it's, so you want, say, the effect of x1 on y, but there's an x2 which causes both of them. If that x2 is not observed and you use OLS, then you get this sampling distribution. You can see it's biased. Okay. If you've got an OLS, if you've got an instrumental variable, that's the red line. So you got an instrument for x2, then you can use that instrument, and then you get this sampling distribution. And as you can see, the variance of the sampling distribution is more than the variance of this. So sometimes IV might be worse than straight OLS. So we say IV is consistent, and that of course depends on the non-testable exclusion assumption. But it's consistent because as the sample size goes up, this is going to converge to the true value. Of course, in the best world, you would have that particular x2. The point is that we're never very sure that we have all the relevant variables, which is why economic seminars tend to be contests between a skeptical audience and a speaker who is trying to assert that he or she has found the truth. Now, one kind of modeling which is very prevalent, especially in the private sector and in industry and in data science as in the popular imagination, is predictive modeling. And this is quite different, and it's come to prominence now. The focus of this type of modeling is to optimize prediction accuracy. So we don't really care why an email filter thinks a message is spam. We only care that the filter accurately trashes spam. And the thing in this is that the techniques which give you very high prediction accuracy, because you can always measure that, right? You predict and then you see what the actual thing was. So the predicted y hat and the actual y can be compared. But the prediction techniques which do a better and better job tend to be more and more like black boxes. Now, one such technique which is really successful is random forests. Random forests build on trees, and a tree is something like this. Okay, so this uses an algorithm. So this is in the context of well switching in Bangladesh. So if we want to predict whether a family is going to switch its well, so if you have arsenic, it's going to lead to health problems if your well is contaminated. So you might want people to switch to a neighboring well, which does. So two things which can affect whether a household switches is arsenic or the distance. So if the arsenic level is low, we go down this tree, and then the prediction is that it will not switch. Or if the distance is high and the arsenic level is high, the prediction is that it will switch. So this is firstly tends in certain cases outperforms things like logistic regression. Then you build on this with random forest, which has got real success predictively, but becomes a little non-transparent. But the tree itself is easy to communicate also. And it's a more natural way to think of prediction. Okay, now I'm going to move to something which is, something you'll encounter far less in journal publications, far less in, it's not a formal way of analyzing, but it's got this man's stamp of approval, Angus Deaton, and he's said this again and again. And in fact, he's publicly criticized random RCTs, criticized in the sense that he thinks that we may be putting too much faith in them. But also what people don't realize is he's also in the past criticized instrumental variables, some of the ways people have used them. He's also, to some extent, begins his book on analyzing survey data by saying that if you're trying to calculate structural parameters, then you are not going, in principle that works, but in practice you end up making a lot of assumptions and it's not very credible. And he writes, it is sometimes more useful to present features of the data, often through graphical presentations, and then to think about the process whereby they were generated. And I find there are some parallels between this and the thinking of Edward Leamer, who wrote the famous paper on let's take the con out of econometrics. So he has a recent macroeconomics book, not so recent, 5-6 years, where he's advocating also, graphing things and then thinking about the mechanisms by which what process could have generated the phenomena captured in your graphical or descriptive statistics. So I'll kind of apply this idea just to also illustrate how one can use this with R. And I find this argument, I've thought about data visualization often. So how can it be useful? So this is just taking this idea and showing you what I feel you can do with it. So you can plot COVID cases with R. The thing about COVID is that there was also what people call an infodemic. The newspapers are full of graphs. Of course, there was a lot of academic output. And there was also publicly available data. Of course, there have been concerns about the accuracy of the data. There's a feeling that it was overwhelmingly underreported and so on, but I won't get into that. So from the Our World in Data website, you can get this data country-wise for COVID. So this is new cases smoothed per million on the y-axis, basically just cases, you can think of it as. And this is the date. So this is the onset in India. This is for COVID cases in India. So this is early 2020. And then we have the lockdown, one of the strictest lockdowns, right? But you can see actually the levels are very low. I think the feeling was that by putting it, you'll just stamp it out. I sense, though no one actually said it, but probably the idea was that you could just and then get a really get a stranglehold on the thing and prevent it. But as it happens, it didn't happen that way. It kind of rose somewhat gradually, and then we had this. And then by about the beginning of 2021, the number of cases, so we all, I mean, I think most lay persons, some, I think specialists, epidemiologists were cautioning us, including some people who saying, you got to watch out type of thing. But whatever. There was also an official meeting, and this is there's a press information bureau documenting this at this date. So there's a briefing of ministers, and one of the officials, it's quite understandable, because if you're not an epidemiologist and specialist, so he actually presented this curve, right? He also presented statistics relating to this situation. So sometimes all the data, if you just go by the current data, right? So that's one of the reasons why we try and inquire about the underlying structure. But anyway, everything indicated that somehow things were fine and we were relaxed. And then all this unfortunate stuff happened. The second wave. And in some senses, I think this is, many countries had several ups and downs. So we had this very smooth thing, and many countries had two waves, but I think it seemed like, we were unique in having this rather subdued first wave, and this, because this is when the Delta variant also appeared. And then it just took off. And then, at least in Delhi, it seems almost everyone got it. Or if it entered one house, then everybody in that house got COVID, it seemed. Okay, so, but anyway, so we had this huge surge, second wave. So now we can go, we've got this basic thing. It's capturing in some ways important facet of the thing. And for a layperson, this exponential rise can seem puzzling, but epidemiologists deal with this kind of thing, right? They deal with epidemics. And one workhorse model is the SIR model, and it's a compartmental model. So in economics too, we have, at the end of the day, we have certain identities, and that anchors whatever models we have. So here you divide the population between people who are susceptible, between those who are infected or infectious, and those who have recovered. So that's the basic SIR model. And a large part of the analytical work in COVID, addressing COVID, now it's hard to say what proportion, etc., but many models, this is the simplest model, and they'll build on. So you have more sophisticated compartments, more sophisticated interactions. But this is really capturing the essence of a lot of the analytical work that was carried out, whether by epidemiologists, ecologists, economists, okay? Not all, but quite a bit. So you can simulate the SIR epidemiological model. When I say you and I mean just ordinary people, not major, it's remarkable. You just have to write a fairly simple for loop, and you can do a difference equation simulation, or you can use the differential equation simulator in R. You can also do it in Excel. So what we get is that the susceptibles goes down, the infections go up. And it's really this interaction between S and I. How does someone get infected? So this is the basic thing, the basic non-linearity in this model is that why we have this is because infections, new infections are happening through an interaction between those who are susceptible and those who are infected. When the number of infected is low, then the number of S star I will be low. And as I increases, S star I will increase. So there's a positive feedback loop. On the other hand, as S increases, as I increases, number of susceptible goes down. So that's a negative feedback loop. So that's why it kind of goes up, reaches a peak, and then tends to fall down. But note that you don't get two waves, of course. So as we know, in analytical models, we try and simplify the world. So it's no surprise that if a generative model doesn't exactly give you this. Now, there is a social scientist, dynamic modeler called Joshua Epstein, who's talked about generative social science. And he does agent-based models, works in epidemiology. So he said that one has to understand that there are two things going on. There's a contagion of the infection itself, and there's the contagion of how we react to that thing. Now, traditionally in economics, we'll have some very complicated dynamic optimization and rational this thing. He says you have fear, and in fear, and then he cites a lot of cognitive work, research. So the thing is that as the level of infections go up, your fear goes up, and everyone on average starts getting careful. Some people like me get very, very careful. But as the infections go down, people relax. So that's one of the reasons. And if you add that into the SIR model like he does, it's a very beautiful paper, I believe, that Epstein has. It's accessible. You get then these two waves. Okay. Now, an empirical thing about this fear is one of the footprints of this fear, for instance, is you can see it in Google Trends. Google Trends are used sometimes to predict flu in the US, etc. And there's a literature on that. But you can work with Google Trends with R. It's quite neat. It's pretty simple to do. There's a G-Trends package. So this is Google searches for oxygen in India and the US. So US I just took as a comparison. So we see US, so this provides a comparison from 2020 to say August 2021. So the line is flat, right? And now look at India. You got this slight up. And then in the second wave, we all saw this, the horrific images, etc. So that's something you can do with, so you can do, there's a lot of work on text analysis with R, etc. That's of course something very data science type thing, sentiment analysis. Now finally, you can communicate with RStudio. You can combine text, code, and output in one document or presentation. You can make interactive web pages. So I'll just show you an example of this. So this is a Shiny app. This is what I mean by an interactive web page. So I was kind of very suddenly, I was into this waves thing, And the interesting thing is that waves don't have any specific definition. We all talk about waves, but I saw a couple of blogs, and there's a paper in Med Archives which said that there is no definition of waves. So if you look at a wave, it's one of those things, like you look at it, you kind of know it's a wave, but how do you, suppose you have data on a lot of countries, which we have, how do you actually collate the number of waves? So you need to define it in some data analytics work. So I thought of a way. Now this Med Archive paper had a rather complicated thing where they fit the model, right? But in a sense, it's ironical because the model they fit is somewhat doesn't, I think, but I'm not sure. But that's a kind of seemed like a somewhat more roundabout way. And I thought of what I thought was a more transparent way. By the way, I must admit that I've tried publishing it, but obviously no one else shares my enthusiasm for this. And also, I guess there's a deluge of papers on COVID-19. So this is the Shiny app. So this is typically, opens up in a browser. And you can select certain parameters, so you can vary it. So span is how long. So if you've got a wave, the idea is it will last, it will tend to be for a certain number of days. Also, a wave will be characterized by some size of the peak, right? You don't want just regular things happening. Now I can select Germany. So if I select Germany, I get this graph for Germany, and then the red is where the peak happened. And this is called an interactive plot because I'm also getting the underlying data as I take my mouse over it, right? So notice in Germany, we had this smaller thing like we had in India, right? We had this smaller thing, all right? And then we went down, and then we had this second wave. So if you look at it, this experience is a bit like India, and this has happened within 2021. So if you only look at, and this is a well-known thing in statistics, if you only look at one, if you have a number of units of analysis, look at all the data, don't just look at one. So if someone had just at that meeting where the Niti Aayog official was, talking about all those statistics at that point in time, if you'd only looked at, for example, of course, this is all in the benefits of hindsight. I'm not saying if I was there, I'd be able to do it. The point is not that, but if you look at this, right, this has happened before that date. So if people were looking at other countries, and in Europe, they did have many waves. Okay, so then I can, getting back to the Shiny app, I can now choose Afghanistan, and now it's showing you the thing for Afghanistan. So this is what we mean by an interactive web page. And then we have this graph, okay? So if you collate all the peaks and the number of waves, so you get all these things. Now, one thing about the data is there's obviously a data reporting issue because the y-axis, the cases smoothed per million vary by orders of magnitude, and that doesn't really make sense. But you get that there are a number of waves. And then we can see that during this 1.5 year period from about the beginning of the thing till about the mid of 2021, what were the number of waves at different all locations in the globe, with a population of over 1 million reported in our world in data. So you can see no waves is very low, one wave is just 23, two waves 60 locations, three waves 47 locations. Now if you change these parameters of how you define the wave, this will change, right? So you can do that sensitivity. So this is what a Shiny web app is. So I'll get back to that point that finally you can communicate with RStudio, and that's very strong in data science or even in policy work. You need to be able to communicate. So you can do all this in RStudio very seamlessly. Now what I've done is I've only scratched the surface. You can do a lot more with R. Thank you.
Thank you so much, sir. On behalf of the Economic Society of Shri College of Commerce, I extend my heartfelt gratitude to you for such an enriching session. It has been an honor hosting you. Thank you so much for joining us today, sir.
Thank you.